Okay, welcome back. Last time we defined enthalpy and talked about some of the relationships on how we can talk about the enthalpy of reaction. And in this video, we're going to get even more deeply into what it means for a reaction to be endothermic or exothermic and how we quantify this enthalpy value. So this is calorimetry and energy flow. This is chapter 6 in your textbook. And let's get going. Okay, so enthalpy is defined as the amount of heat that is absorbed or generated when a chemical reaction occurs. And remember that this is because we are assuming that chemical reactions do very little work. That they stay the same volume during the course of the reaction. Now, the key with delta H of reaction, so the enthalpy of a reaction, is that it reflects the stoichiometric amount of reactants and products for the reaction as is written. Okay, so we're going to talk about what that means. But the stoichiometry of the reaction is going to be very important when we start thinking about this enthalpy of reaction. So this means, so what we do is we write these reactions as the chemical reaction. So this is the combustion of propane. And when we combust propane, the reaction gives off I know it gives off because this is negative. Negative delta H means it is exothermic, which means that the system is giving energy to the surroundings. So this is exothermic, it's giving off heat, and it's giving off 2,044 kilojoules of energy. But that energy is for 1 mole of propane reacting with 5 moles of oxygen. And so this energy is for the exact amounts of chemicals that are indicated in this reaction. And so, as our example, we have a gas tank is filled with liquid propane in a home barbecue. It contains 13.2 kilograms of propane, and we need to calculate the heat associated with the complete combustion of all of the propane in the tank. So now we no longer have 1 mole of propane. And so what we're going to have to do is we're going to have to use this delta H of reaction as a conversion factor. And so this delta H of reaction is per 1 mole of propane. And this helps us think of this as a conversion factor. So to do this problem, I would take 13.2 kilograms of propane. And in 1 kilogram, there are 1,000, not 100, 1,000 grams. And now I have to convert from grams of propane to moles of propane. And so I use the molar mass, which is 44.09 grams in 1 mole. But now I need to go to energy. And so that is where I use this delta H of reaction, that I know for 1 mole of propane, I get a negative 244 kilojoules of energy. And so if I solve this, I get negative 6.12 times 10 to the 5th kilojoules of energy out whenever I burn all of the propane in this tank. Now, if I were looking at a different reaction, say I'm going to give a generic reaction that is 2A plus 3B goes to form C. And my delta H is a positive 243 kilojoules. This delta H is per 2 moles of A. And so that would change this conversion factor here. And so notice how this conversion factor is dependent upon the stoichiometry of the species that you're interested in. We can also write this delta H for my hypothetical reaction as positive 243 kilojoules per 3 moles of B. This one up here, I could write as negative 244 kilojoules per 5 moles of oxygen. And so it really depends upon what conversion you are trying to use as to what stoichiometric coefficient you are going to pull to help you solve the problem. But know that as written, this delta H of reaction is for the reaction that is given to you as it is written with that stoichiometry. Okay, so from here we're going to keep working with delta H's, and I'll keep showing you more examples of these types of problems. So keep up the hard work.